Hello, everybody. Today we will learn how to draw Lewis structures, right? So let me write that down. Today the topic is Lewis structures. Right? So the idea of drawing Lewis structures is to have an octet of electrons or 8 electrons around each element we have in that molecule. Uh, and then we always have an octet of electrons in carbon, nitrogen, oxygen, and fluorine atoms in a molecule. And then other atoms in a molecule like hydrogen can only have 2 electrons because it has only one shell. And when it comes to other elements such as sulfur, phosphorus, they can have more than 8 electrons around it. But we're gonna try to have 8 electrons. But if it has to violate that octet rule, they can violate because they have access to this D subshell because they are in the third shell. Okay, so strictly speaking, there are only 4 elements in the periodic table that follows the octet rule strictly. Those are carbon, nitrogen, oxygen, and fluorine. All the other atoms can violate the octet rule. But anyway, so we'll stick with the octet rule when we draw the Lewis structures. So to start with, what we want to do is we're gonna learn by doing some examples here. First, we're gonna start. Let's start with carbon dioxide. So carbon dioxide or CO2. So we have carbon and we have oxygen atoms here. The first step in developing Lewis structures is to count the valence electrons. So carbon is in the fourth group. You can see we have 4 over here, meaning we have 4 valence electrons. So I'm going to write we have 4 valence electrons from carbon. And oxygen is in the 6th group, meaning they have 6 valence electrons. We have 2 of them. 2 times 6 is 12 electrons. So altogether, we have 12 plus 4, 16 valence electrons. I like to boil this down to the number of pairs of electrons. So 16 electrons is 8 electron pairs because 16 divided by 2 is 8. Okay. And after counting the number of valence electrons, the next step is to draw the skeleton of the molecule. So when we do that, we write the atom with the higher bonding capacity at the center. So in this case, carbon has a bonding capacity of 4. So that would be in the center. And then the oxygen atoms, which has a bonding capacity of 2, will be bound to it via bonds. Okay. So now this is the skeleton of the molecule. This is the minimum number of bonds we should have for us to have a compound that contains carbon and 2 oxygen atoms. Now what we do is after determining the skeleton, we're going to distribute these 8 electron pairs starting with the outer atoms. We already have 2 electron pairs because we have 2 bonds. Each bond is 2 electron pairs. Therefore, we have 2 electron pairs already here. And therefore 1, 2, yes, 3, 4, 5, 6, 7, and 8. That's the third step, distributing the number of the electron pairs we have in the skeleton, starting with the outer atoms. Now we see that carbon did not get any lone pairs at this stage because we have already distributed our 8 electron pairs between the 2 oxygen atoms. And now the fourth step in drawing Lewis structures is to count the electrons around each atom. Now we see that around oxygen we have 3 lone pairs, that is 6 electrons, and then 1 bonding electron pair. So let me mark them. Here's 1, 2, 3 lone pairs, and then 1 bonding electron pair. That means 4 pairs of electrons. If you have 4 pairs of electrons, that means we have 8 electrons around oxygen. Same thing with the other oxygen as well. Because we have 1, 2, 3, 4 pairs of electrons, meaning we have 8 electrons around oxygen. So oxygens are oxygens have fulfilled the octet rule. But when it comes to carbon, we only have 2 bonding electron pairs. That means we only have 4 electrons. We need 4 more electrons around this carbon atom. And how do we get that? We get that by delocalizing some of these lone pairs from oxygen like this to make a double bond. And when that happens, we're going to get carbon double bonded oxygen with 2 lone pairs, and carbon double bonded oxygen on the other side, 2 lone pairs. Now, if we count the electrons again, we see that we have 1, 2, 3, 4 electron pairs around oxygen. That means we have 8 or octet of electrons around oxygen. And around carbon, we have 1, 2, 3, 4 bonds. That means 4 bonding electron pairs, meaning 8 electrons around carbon as well. So we have octets around all the elements in our molecule. Therefore, this is going to be the Lewis structure of carbon dioxide. All right, and that's how we draw Lewis structures. And then let's try a few other molecules, maybe at least 2. So to do that, let's get rid of carbon dioxide, and then let's have another molecule like, let's say, NF3. Okay, so let's say our molecule is NF3. Okay, again, first step is to count the valence electrons. Nitrogen is in, let's see, nitrogen is in the 5th group, meaning it has 5 valence electrons. Fluorine is in the 7th group. You see number 7 here. That means it has 7 valence electrons. Okay, and we have 3 fluorine atoms. That means 3 times 7, 21 electrons from the fluorine atoms. Altogether, we have 21 plus 5, 26 electrons, meaning 13 electron pairs. And once we have this, the next step is to draw the skeleton of the molecule. The skeleton, in the center, we're going to have the element with the higher bonding capacity. In this case, nitrogen has a bonding capacity of 3, and fluorine has a bonding capacity of 1. Therefore, nitrogen is in the center, and then we're going to have 3 fluorine atoms bound to it via bonds, covalent bonds. And now, once we have that, what we do is we need to distribute the 13 electron pairs, starting with the outer atoms. We already have 1, 2, 3 electron pairs as 3 bonds. Therefore, we're going to start with this fluorine over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we see that fluorine already has 8 electrons around them. That means the 13th electron pair should go on top of nitrogen. Okay, if we count the number of electrons around nitrogen, nitrogen has 1 lone pair, and then 3 bonding electron pairs, altogether 4 electron pairs, meaning 8 electrons around it. Therefore, nitrogen has an octet as well. Okay, and then fluorines also have octets. Just to count that, we have 1, 2, 3, 4 electrons around 4 electron pairs around oxygen, fluorine, meaning we have an octet around fluorine atoms as well. Okay, so that's NF3. We can do another molecule. Let's do a molecule that has more than 2 types of elements. Let's do something like CH2O. Okay. So CH2O. Again, step 1, count in the valence electrons. Okay, so we have carbon. Carbon is, give me a second, carbon is over here in the periodic table in the fourth group. That means 4 electrons. And then we have 2 hydrogens. Hydrogen is in the first group, meaning 1 electron. We have 2 of them. Therefore, 2 electrons from 2 hydrogens. And then we have 1 oxygen atom. And oxygen is in the 6th group, meaning we are going to get 6 valence electrons from oxygen. And then if we all together, we're going to see that we have 12 electrons, 12 valence electrons in this molecule. That means 6 electron pairs. Once we count the number of valence electrons, the next thing is to draw the skeleton of the molecule. Again, at the center, we're going to draw the atom with the higher bonding capacity. In this case, it should be carbon with a bonding capacity of 4. To that, we have an oxygen bound and then 2 hydrogen atoms bound. Okay. And then what we're going to do is we can distribute the 6 electron pairs starting with the oxygen because hydrogen can only have 2. It already has 2 electrons around it. Therefore, we cannot add more lone pairs to hydrogen. Therefore, all the lone pairs first should be added to the oxygen. Okay, so we have 1, 2, 3 electron pairs already in these 3 bonds. And then here's my 4th, 5th, and 6th electron pair. And once we do that, we see that we have an octet of electrons around oxygen, but around carbon, we only have 3 electron pairs. 3 bonds means 3 electron pairs, meaning only 6 electrons. So what we can do is we cannot add more electrons now. The only thing we can do is we can delocalize to form bonds so that they can share electrons to have octets of electrons. So the only possibility here is we can have this one of these lone pairs from oxygen delocalized between oxygen and carbon to form a double bond. And when that happens, it's going to form this structure, which is the Lewis structure of this compound. Okay, because at this point we have 8 electrons around oxygen because 4 electron pairs, and then around carbon also we have 8 electrons. Okay, we have 1, 2, 3, 4 bonding electron pairs, meaning 8 electrons. That means all the atoms in this molecule except for hydrogen has an octet. Hydrogen has its full capacity of the shell, which is 2. So this is going to be our Lewis structure for this molecule. All right. Maybe one last molecule, maybe with, let's see, we can do, all right, let's do something that includes a weird molecule, a weird atom, okay? So let's say that we want to draw SF4. You know what? Before SF4, let's do SO2. Okay. Again, the first step is to count the valence electrons. Okay. So sulfur is in the 6th group, meaning 6 valence electrons. Oxygen is also in the 6th group, 6 valence electrons. We have 2 of them. There are 12 electrons. And meaning we have altogether 18 valence electrons. That means 9 electron pairs. Okay. Now here's the thing. In this case, sulfur and oxygen have the same common bonding capacity of 2 because they are 2 groups away from the noble gases. However, we're going to draw sulfur in the center here. The reason is when we have the same bonding capacity, then we're going to draw the larger atom at the center. Okay. In our skeleton, and then we have the 2 oxygens bound to it via bonds, and here's our skeleton. All right. Then once we have the skeleton, we're going to start distributing the electrons, the 9 electron pairs, starting with the outer atoms, which are oxygens. So we have 1, 2, 3, 4, 5, 6, 7, 8, and the ninth should go here. Okay. And now what we can do is we see that we have an octet of electrons around oxygen because 3 lone pairs and 1 bonding electron pair means 4 electron pairs altogether, meaning 8 electrons. But around sulfur, we have 1 lone pair and 2 bonding electron pairs, meaning only 3 electron pairs. That means 6 electrons. We need to delocalize a lone pair from oxygen. So we have two possibilities here. We can either delocalize from this oxygen or from this oxygen. Okay. So as a result of that, so we can have two possibilities. I'm going to go down here now. If we delocalize from, say, the possibility 1, then we are going to get this structure. Okay, where we have octets around each element. But if we delocalize from the second possibility over here, then we are going to get this structure where we have the double bond on the other side. Okay, so these are two possible Lewis structures for the same molecule. Okay, so whenever we can draw more than one Lewis structure by moving only the electrons, like in this case, we just moved only the double bond, we say that that molecule shows resonance. Okay, so that means it can be, so we can have these two possibilities for the Lewis structures. Therefore, this molecule shows resonance. So the significance of resonance is when we have resonance, the experimental structure is a structure in between them. Therefore, we can draw what we call the hybrid structure, where we have sulfur in the middle, and then we have two oxygens bound to it like that. But this bond, let's say on the left hand side, can be either a double bond or a single bond. Okay, so here is a double bond, here is a single bond. Okay, so that means this bond has both double bond and single bond character. So we're going to draw it like that. Same thing with the other bond, right? So here is single bond first, yellow, single bond in the first Lewis structure. In the second Lewis structure, it's a double bond. Again, that bond also has double bond and single bond character. Therefore, we're going to draw it like that. So that what this means is this bond is between a single bond and a double bond. Okay, and this is called the hybrid structure of the molecule. Hybrid structure of the molecule. And note that we do not draw the lone pairs in our hybrid structure. And then these structures over here, okay, are called resonance structures. Resonance structures. All right, so that is that. Maybe if we can, I think that should take care of the Lewis structures. We will do SF for some other day. It's a fun one to do, by the way. I'll give you a hint. It has a weird geometry. Okay, we'll do so. Therefore, we'll do this when we talk about the geometries of molecules. For now, I hope this video helped to refresh your knowledge about drawing Lewis structures. And I'll see you guys in class. Bye, everybody.